Okay, ladies and gentlemen, welcome to physics. We're going to look at space physics, and this is for students who are studying separate sciences. And I'm going to use Miss Naressi's favourite colour pen, okay, which is brown. So we're looking at space physics. Now, and this is for separates only, so that would be E1 and A1. Now, when we're looking at space physics, there's 4 key areas that we really need to think about. There's our solar system. Okay, we also have how our planets are kept in place. So we're looking at the forces there that hold the planets in place. We're also looking at the life cycle of stars. And we're also looking at essentially redshift. And that's basically the idea we have about the expanding universe. Okay, so there are key main areas. But let's start off by looking at our solar system. Now, in our solar system, everything is kept in place by the sun. And the first planet that's closest to the sun is Mercury. Then we have Venus, our planet, Earth. We have Mars. We have a larger planet, which is Jupiter. We then have a large planet with the rings that go around it, which is Saturn. We have another planet called Uranus. And then finally, we have the planet Neptune. Now, there is one other small dwarf planet called Pluto. I'm going to put it down here because it's not a planet really. Okay, that's in the Kepler belt, out on the outer reaches of our solar system. Now, those are the planets in our solar system, but we need to actually think about where we are in relation to our position in the universe. And we actually live in the Milky Way. Okay? And that's not a treat you can eat between meals without ruining your appetite. Okay? Now, we're actually on one of the arms of the Milky Way. So it's a spiral galaxy. It looks a little bit like this. And we're out on that outer edge there. Okay? So the first 4 planets are rocky planets. And they actually are what we call the inner planets. And then we've got the 4 outer planets. And they're mainly gas giants. We're not quite sure how they're actually made up. So there are our solar system. Now, I'm going to actually look at how our solar system and the planets in our solar system are actually kept in place. And for this, I'm going to put our sun right at the center. So there's the sun. Okay, and the first planet that orbits the sun is Mercury. So here it is, I've drawn it here. And Mercury will go around the sun. Now, this is something that's called centripetal force, and we need to understand, well, how does the sun keep the planets where they are? Now, we actually say that they're held in place by gravity, and it's the gravity of the sun that holds it in place. But every planet is in a different orbit, and therefore every single planet is going at a slightly different speed and has a different number of days that make up their year, okay, for going around the sun. So if for the purpose of this diagram, if we actually say that the dot right in the center of the sun is the axis around which everything else rotates. Now, gravity pulls Mercury to the center of that axis, okay? That's the force that's holding it in place, all right? And it is traveling around the sun, okay, as you can see with these green arrows, in that direction, okay? Now, every single planet has velocity. And velocity, okay, as we know, is speed in a direction. This is the velocity. If gravity suddenly stopped from the sun, it disappeared, okay, Mercury would not carry on in that circular orbit. It would actually be fired out in a straight line, okay, away from the sun, and would continue going, okay, for absolutely ever until it ran out of energy, okay? Now, so going around is the orbit. Okay, we are going around an axis, and gravity is the force that's providing the centripetal, okay, force that holds us in place. Now, planets are in different orbits. So if I put the other planets, so we've got Mercury, Venus, Earth, and Mars, we all orbit, okay, the Sun, which is here in the middle, okay, but it takes different amounts of times. Now, centripetal force increases if mass increases. So the force to hold a bigger planet in place has to be bigger if the mass is bigger. If the speed increases, so does the centripetal force, okay? But if the radius of the orbit decreases, okay, we also get an increase in centripetal force. Now that principle we actually use to keep objects orbiting our planet Earth. So I'm going to do planet Earth here, because we're a green and blue planet. And orbiting around planet Earth, we have satellites. Now, the first one is a natural satellite, which is called the Moon. And the Moon, again, is orbiting the Earth. There's its orbit. And it's orbiting the Earth because the Earth has gravity that is holding it in place. And again, like we did with the last diagram, if the Earth disappeared or lost its gravity, it would actually fly off because of its velocity in that direction. So the Moon's velocity is always changing as it goes around planet Earth, okay? But the Earth has a gravity to hold it in place. And that's one of the characteristics of a planet, okay? A planet is something that has enough gravity to hold things in place. So all of our other planets that we drew, okay, here, will actually have moons. Jupiter has a lot of moons. So does Saturn, Uranus. There's the Earth, okay? They're big enough to actually hold other objects in place. Pluto, which is a dwarf planet, doesn't have enough gravity to hold other objects around it. Okay, so that's why we don't classify that as being a true planet, although it does look very much like a little planet. Okay, now that's a natural satellite. However, we also have other satellites that orbit planet Earth. Okay, so I'm going to draw this as a little box there with some little wings. Can you tell me what it is yet? Okay, it's a artificial satellite. So these are things like the communication satellites. So there is beaming information backwards and forwards to planet Earth, for example, like Sky TV. And just remember that the way that it does that is by microwaves, because they can actually easily cut through the Earth's atmosphere. So this whole idea of centripetal force, okay, is holding objects in place. It's holding the planets in place, it's holding satellites in place, okay? And the acceleration around every object is always increasing, and that centripetal force is caused by gravity. And gravity, and having enough gravity, is what makes a planet actually a planet and not a dwarf planet, okay? Now, we've looked at the solar system and the objects that are in there, and we've also looked at how planets are actually kept in place, all right? But let's just have a little moment looking at our sun. Now, our sun is absolutely vital. Our sun is a star, and it's the only place where nuclear fusion takes place, okay? Now, within our sun, we have the following things that are happening. Hydrogen atoms are joining together with other hydrogen atoms to make helium, okay? Helium atoms are joining together to make all elements up to iron, okay, and including iron. So literally every element on the periodic table up to and including iron are actually created within a star, like our sun, okay, which is a small, medium-sized star. All elements that are heavier than iron are created in a supernova and distributed across the whole universe. And we'll come on to what actually happens in a supernova. So remember, everything up to and including iron is made within a star like our sun, and all the heavier elements are actually created within supernova. Now, we're going to look at the life cycle of a star, okay? And before we do, we need to really think about where stars actually come from. And stars actually come from big clouds of hydrogen gas and dust called nebula. Okay? And nebula are basically the birthplaces of all stars. Now, how does a star actually start to be created? Well, what actually happens, all of this gas that's dotted around everywhere starts to come together. And as it comes together through gravitational potential energy, okay, it gets closer and closer and closer, and that creates thermal energy. Okay, so as that thermal energy is increased and the gravitational potential energy increases, that's where we get the birth of a protostar. So that's basically the start of a star, this whole process. Okay, and when there's enough thermal energy and there is enough gravitational potential, and we start to have fusion taking place, that is when we get what's called the main sequence. Okay, so a nebula becomes a protostar, fusion starts to happen, and it becomes the main sequence. And our sun is currently in its main sequence. Okay, now our sun, okay, has got a tremendous amount of forces taking place, because as these hydrogen atoms are hitting each other, colliding, hitting each other to make helium, helium are hitting each other to make other elements, okay, we're giving out a massive amount of energy. And our sun is, in its main sequence, is in equilibrium. And what that actually means is that the forces of gravity, or the gravitational potential energy, pulling the particles together, are equal to the actual forces of expansion by the fusion energy. So that's really critical. So if they actually ask you what's actually happening within a main sequence of a star, you actually need to be able to say that in the main sequence there is an equilibrium, because the gravity or gravitational potential energy pulling the gases into the star is equal to the rate of expansion caused by the fusion energy that's actually being given out. Okay, so it's really quite important that we get that. So if we go to a new card and let's just put our main sequence in there. So we have nebula, spell it right, nebula to a protostar to the main sequence. Now, boys and girls, this is where size matters, okay? The bigger you are, you're going to die differently. The smaller you are, you're going to die differently. So we have our main sequence. Now, if you are a star that's small, like our sun, okay, you are going to become, okay, a red giant. If you are a very large star, okay, much bigger than our sun, you are going to be a red supergiant. Okay, now as you start to die, okay, fusion, you're running out of fuel, okay, so you're going to get bigger and redder and cooler, and you're going to expand, okay? And this is where you're going to be making more and more of those heavier elements, all right, up to and including iron. Now, if we take a small star and its death, so we go from being that red supergiant, okay, we then become, let's get a better pen than that, we become a white dwarf. And that one's not very good either. I think we'll give up on those orange ones. We become a white dwarf, okay? And what that actually means is that gravity, just make sure that's on the page, gravity, okay, pulls all of the matter inwards. We reduce the amount of energy there, we become much, much denser, and after we've given out all of our energy, we become a black dwarf. Once we're a black dwarf, we're virtually invisible to the universe. We're not giving out any more energy. We're really dense. We're at the centre of our solar system. We still have a massive amount of gravity, but we're not giving out as much energy at all. However, when you are a red supergiant, you actually die, you expand, you lose energy, and you actually become a supernova. Okay? And that's when you actually explode. And as you explode, you make all those heavier elements that go out off into space. Okay? Now, dependent on your size, what remains can be one or two things. It can actually be a neutron star, or you can become a black hole. So if you're absolutely a massive, massive, massive star, you will die and eventually become a black hole. If you're not quite as big, you'll become a neutron star. But the key thing here is this whole idea of being a supernova, okay? So if you're a supernova, okay, you're going to make all those big elements higher than iron that go out into the universe. And that's why people often say we are made out of stardust, because all the elements above hydrogen actually are made within stars, okay? Now, the final thing that we need to really go through for this topic is redshift, okay? Now, redshift is something that provides evidence that the Big Bang actually took place. And in order for us to actually know what redshift is, we've got to think of the Doppler effect. Now, what does the Doppler effect actually say? What does it mean? Well, it's the apparent change in the frequency of a wave caused by the relative motion between the source of the wave and the observer. Okay? All right, now that's quite a mouthful. It's the apparent change in frequency between a wave caused by the relative motion between the source of the wave and the observer. Okay, so in other words, you can experience this when you have something like a car coming past you. So if you hear a car coming up to you and then it goes past, you hear a sound a little bit like meow, meow. And that's because the sound is changing. Because here is if this is you, okay, and this is your car, okay, as it's moving towards you at speed, okay, the sound waves in front of it are squashed together, changing its frequency. But when it goes past you, okay, as it's zooming past, the sound waves are more spread out, okay? That's the Doppler effect, okay? Now, the same thing happens to the frequency of light when an object that's emitting light, okay, is moving towards you or moving away. So let's think about what that would mean for us on planet Earth. So there's us on planet Earth. Okay. Here's Mr. Schuller, because I know Mr. Schuller actually loves to do some astronomy. So I'm giving him a telescope. Okay. And he's looking out into the night sky. Okay. And what he can see is he can see two stars. He can see a star here that's giving out some light. There it is, okay, in the night sky. And he can see a star here giving out some light in the night sky. Now, if we actually had a ruler and we could put that onto our diagram, we can actually see that the distance to star 1 is shorter than the distance to star 2. Okay. Now, when we actually look into the night sky, we suddenly look at these planets and we go, oh, they're slightly different colours if we compare them to our sun, which is close by. So there's our sun that we see in the sky. It's close by, and we go, hey, we look at that and the colours are slightly different. Now, when we compare the light to our sun, all right, we know that the light that suns give out is the same, but we actually can go, well, this star, its light is red-shifted. And what that actually means is that because it's moving away from us at speed, the light that it's giving out is being stretched. Okay? And as the light is being stretched, it means it looks a little bit more red, or towards the red end of the spectrum. Whereas this star here, it is still moving away from us, but it's closer to us, so its light isn't quite stretched as much. So we can see the difference here between the wavelengths of that light and the wavelength of this light. So this one might, for example, be a little bit more orange. Okay, so as an object is moving further away, okay, at speed, its light is being red-shifted, or basically stretched. So it looks more on the red end of the spectrum. And if we remember the spectrum, okay, it's red, orange, green, blue, indigo, violet, okay? Red, orange, green, blue, indigo, violet. And the reason why I've done that is because this has got the shortest wavelength. And as we go towards the red, okay, it has a longer wavelength. So it gets stretched to the red end of the spectrum. Now, this gave us some evidence for the whole Big Bang Theory, that everything starts at one point and exploded out from that point, and the universe is continuing to be stretched, okay? Now, all I really want to do is to finish off with one key thing that sometimes they actually use about Redshift, okay, on your exam, all right? And this is the thing that I just want to go through with you. So I'm going to take up my green and my brown pen, okay? So they could say, here is a spectral diagram for what our sun looks like. So when we look at the sun, we look at our sun, and these are the points on them, okay, of specific frequency of light, okay? And then they might say, well, this is a sun. Let's call it sun 1, okay? And this is its spectra. Okay? And then they could give you a second sun, sorry, which looks like this. Okay? Now, they could say to you, all right, from those diagrams, what can you tell me about, all right, the spectra of the different suns? So if they actually said that this one is red here and this one is violet, okay, and that's what our sun looks like, would sun 1 be redshifted or not? Well, because these lines are further this way, okay, you would actually say, yeah, they've all moved more towards the red end of the spectrum. So this is red shifted, okay? So it is moving away from us, okay? All right. Now this one, okay, if they said, well, could you compare sun 2 to sun 1? You would actually say that sun 1 is closer to the, sun 2 is closer to our sun because its lines are, okay, more towards the blue end of the spectrum, okay? So that's one of the things that they could potentially ask you on the exam to look at from the spectrum, which is redshifted, which is not. The other thing that they could give you is they could give you an example of, here is two suns that are rotating around a single point within a star. You're here, so I'm going to put Mr. Schuller here again, okay, and he's got his telescope out looking out there, and the stars are moving around this fixed point in this direction. And they could say, okay, can you describe what kind of shift would you see for star 1 and star 2? Well, because star 1 is moving away, we would say that would be red shifted. And because star 2 is moving towards, we would say that is blue shifted, okay? Because moving away, the light is going towards the red end of the spectrum. Moving towards us, it's going towards the blue end of the spectrum, okay? So that really gives you a summary of the main factors of space physics. Thank you very much.